Okay, I'd like to explain some things for Chapter 5 and 6, specifically a relatively new formula sheet and some additional material I've provided on Blackboard that will make your life much easier when it comes to solving problems in Chapters 5 in particular, but 6 also. First, if you go to Blackboard, go to PowerPoints, Videos, and Docs. You'll find the folder for Chapter 5 and 6. I'm going to open that in a new tab. Here's the formula sheet that was revised March 1st. And the first part is Chapter 5, Discrete Probability Distributions. And these three formula right there are the material that is in the first part of Chapter 5. So in the Jaggia and Kelly book, this is basically the material from page 150 through 162. We do not cover section 5.3, portfolio returns. This is the formula for the expected value. This is the formula for the variance. And this is the formula for the standard deviation, which is and always has been and always shall be the square root of the variance. The next set, where it says binomials, is section 5.4 of the Jaggia and Kelly book, the binomial distribution. And they give you the formula that's indicated there, and they also give you the expected value, or the mean, the variance, and again the standard deviation, which is just the square root of the variance. What I give you in addition to this formula is very important. If you scroll down to this part, you'll see binomial and Poisson tables. Click on that, and when it opens, there will be tables that basically allow you to use the table as opposed to using that rather large and complex formula that is on page 168 of the book and the first part of the formula sheet that I just pointed out. There's another video on how to use binomial and Poisson tables, so I won't repeat that. But for example, if you have a binomial problem with a constant probability of, say, 10%, the sample size is 5, those are your probabilities there for all values of x 0 to 5. Then the question may ask you, what's the probability of exactly 2? 0.0729. What's the probability of less than 2? That's 1 and 0, so you would add those two together. And that's how the binomial tables are extremely helpful to you as opposed to using that big formula. So please be aware that the binomial tables are available to you on Blackboard, and you should use them during the test. It might help you, in fact, to print those out as opposed to trying to look at them on the screen while you're taking the test. The expected value or mean for a binomial problem is provided there. The variance, standard deviation, which again, just the square root of the variance. Next section under discrete probability distributions is the Poisson. This is covered in your book on page 173 to 178. Note we do not do section 5.6, the hypergeometric distribution. There's the formula, there's the expected value, there's the variance, and there's the standard deviation once again. If you go back to those tables after the binomials, and yes, you have to page through them. Here's table 6, which is just values of e to a power. You can avoid that. But here are Poisson probabilities. And once you read through the Poisson section, you'll learn that Poisson problems work with a constant mean that might vary per interval. So if you have 6 per mile, you'd have 3 per half mile, you'd have 1.5 per quarter mile. Once you have that, if you have 1.5 per quarter mile, what's the probability that x equals 2? There it is, 0.2510. What's the probability that x is less than 2? I would add those two numbers. So again, the Poisson's table works similar to the binomial, only the difference is you don't have a value for little n, and you don't have a probability, you have a mean. But that's a Poisson problem, and that's how that works. So going back to the formula sheet, there you go. You might say, well, what do I do if my mean is not on the table? Let's say my mean is 1.65. Well, then you do have to use that formula. But I think on most of the problems in the homework, and I'm not sure, but most, if not all, the problems on the test similarly use a number that you can rely on the tables to solve a Poisson distribution problem in Chapter 5. The next part of the formula sheet is for Chapter 6, continuous probability distributions. And frankly, the normal and exponential curves are explained pretty well in the book. Some of the way the problems are written in Chapter 6 for normal distributions is not particularly helpful or clear, but I provided additional direction on those in a section here on Chapter 6 on Blackboard of understanding Chapter 6 problems. But let me get to the uniform, because this is relatively new, and I didn't get this out of the book. I made this up pretty much myself. The expected value or mean is right there, a plus b over 2, and the standard deviation is there, b minus a squared over 12, square root of that, to get the standard deviation. What's new is this line, the probability formula. The probability of a uniform distribution recognizes that the distribution for a uniform continuous probability problem is a square or a box. And we find areas of a box by taking base times height. So here we have a uniform continuous distribution. The lowest point on this box is designated by A. The highest point in this box is designated by B. The height of the box is 1 over B minus A. Here is that new formula, so to speak, and it says the probability of x is equal to the base x2 minus x1 times 1 over b minus a, which is the height, for any value where x1 is going to be equal to or greater than a, and x2 is going to be less than or equal to b. I could technically, instead of a comma there, could have put a greater than sign to indicate that x2 will always be to the right of x1. So looking at the blue box here, the probability would be x2 minus x1 times 1 over b minus a, base times height, 100%. That's all the box. Of course, that's not how problems will come to you in this part of Chapter 6. Instead, it will come something like this. I want to know the probability or area of the yellow box. Therefore, I'll find that by the base area of concern or of interest. That's x2 minus x1. So whatever that value right there for x2 is, subtract by x1, that's the length or distance of my base, times the height, which is still 1 over b minus a. And that will give me the probability of this area. So just say, for instance, if I had a height of 0.25 and a distance here of 10, where x1 was 10 and x2 was 20, that's a distance of 10, and I think I got to remember what I said my height was. Let's say again my height is 0.3, then that probability area is 30%, that yellow area. Similarly, sometimes x2 might equal exactly b and x1 there. Similarly, I could have moved this area over here where a and x1 are the same, and right there would be x2. It'll just really depend where that area of interest is that you're looking for, and you'll just multiply base x2 minus x1 times height 1 over b minus a for all uniform continuous probability distributions. So going back to your formula sheet, that sort of explains this new formula. Note it says 0 elsewhere. I think that's explained fairly well in the book. If you have any questions, look at page 193. Any area to the left of A in figure 6.1 has a probability of 0. An area to the right of B in figure 6.1 also has a probability of 0. Finally, the last thing to explain is exponential. Exponential is covered in section 6.4 of the book. And note, we do not do log normal distributions, which start on page 216. We limit it just to exponential for this part of the problem. And the exponential distribution formula is explained on page 214. One thing the book does, not sure why, it says that I have this Greek symbol lambda, which is equal to 1 over mu, or the average. And then it says, okay, the probability distribution function is 1 minus e to the negative lambda times x. If you just replace lambda with 1 over the mean, you get this formula right here. 1 minus e to the negative x over the mean. And when you calculate that using your calculator, I would use e exponent negative open paren x divided by mean closed paren equals, just to make sure that x divided by mean is one calculation. Notice also this part of the formula, it says all values of x are greater than 0, because unlike the uniform continuous and the normal continuous probability distributions, the exponential cannot cross the vertical y-axis. It always butts up against the y-axis, and a value for x never is negative or below 0. So hopefully that'll explain the new modified formula sheet to you, and frankly this also provides a great overview of chapter 5 and 6 and the material in there. Chapter 5, discrete probability distributions, will be one of these three. A distribution with probabilities assigned through a relative frequency or subjective measure. Binomials, where we have 4 characteristics that must be true. Most importantly, the trials are independent, there are n trials, and the probability of success remains constant. And the Poisson, where we have a constant average over a length of time or space. For the continuous, it's going to be either uniform, which is presented by a curve that's the shape of a box, it is a box, a normal distribution, which is a bell-shaped curve, and you use the tables that are in your book, specifically Appendix A on page 730 and 731. And exponential, where we have no tables, it's just a math calculation. That should be that overview. Good luck on chapter 5 and 6, and if you have any questions, please let me know, or post on Blackboard, Ask Professor Paulson. Thank you very much.